All right, welcome everyone to my webinar, How to Model Losses and Damping in Ultrasonic Transducer Finite Element Simulations, particularly in dynamic simulations or frequency analysis. I'm going to be discussing, get that out of the way, oops, what happened there? All right, I'm going to be discussing the importance of damping. Okay. And also, why do we care about damping and ultrasonic transducer performance? And then obviously, then what is it going to do for us in our simulation? I also discuss theoretical and experimental treatment. Basically, I'm going to be measuring a transducer's quality factor and using that both in a high power and low power scenario, in an unloaded and unloaded scenario, and use those values in order to properly simulate the transducer to the best of our abilities. In COMSOL, and I'll also explain an analysis type that works in ANSYS and how do you put those losses, because they're really not so friendly. Last time I checked in ANSYS, you have to do like a one line of code, but it's not kind of a built-in thing. So I'll implement those quality factors for the transducer. If there's time, I can also discuss viscous and elastic damping, and basically why is the method that we're using for damping of these transducers, basically the crystals, the interfaces, the metallic components, why is that accurate versus perhaps some things or some formulations that we may have been taught originally when we studied, harmonic oscillators and damping and dash pots and stuff like that. So I'll just speak a little bit about my company and then kind of move on to the technical stuff. My company is Ultrasonic Advisors. My name is Hussein Shakani. I'm the founder and consultant in my company. I've experienced in many different areas of ultrasonic transducers, expert in the use of piezoelectric materials or ceramics in many different applications, not just for Langevin transducers, bolt clamped, but also for many other types of devices. I have consulted in, and I'm continuing to kind of explore new projects and explore my expertise there. In particular, I perform finite element simulations using COMSOL for my clients, but I have a whole host of other kind of expertise areas, including those listed here. I do believe in a kind of a holistic approach to ultrasonics. You can't do simulations if you don't know experiments, for example. And in the same way, if you don't know, if you do simulations, if you do experiments, but you don't really have a deep understanding of the theory or why the device is behaving as it is, then there's going to be some big chunks missing when you run into problems. So yeah, back into the outline of the presentation today. We're going to be talking about how to model losses and damping in ultrasonic transducer finite element simulations, specifically in dynamic simulations. This won't be able to cover everything, but I think it covers a whole lot of what you need to know practically to implement damping. And then I guess the questions that come after are those that come after. But this would be a good straightforward way to go about it. So as I mentioned, I'm going to be showing an experimental portion, which is already pre-recorded. So don't worry from the kind of mess ups I had last time with the USB cord getting unplugged and everything during the presentation several times. I'm not going to be doing that live, but I have it recorded. And also, I'll be doing simulations with the COMSOL, and I'll ask kind of you guys how much detail do you want me to go? Do you want me to set up the model from the very beginning, or would you like me to simply just kind of start with the finished model and just explain from there? I guess that it also depends on how much time I take and how much I talk. But I'll discuss a couple of areas that's the low and high power quality factor, which some people may be unaware of how low and high power works. And power is relative. There's no specific number or energy density or power density. It's just specifically for your device. What tends to happen if you measure at very low voltages and power levels, you'll tend to get you'll tend to have a condition that you can consistently measure the product performance in the same way. You get the same quality factors. However, when you increase the power, then the losses increase due to physical mechanisms. Those mechanisms are usually not explicitly put in a simulation program. There are ways, but it's typically not done like that. So I'll just be I'll just be talking about those two and how you would analyze that, and maybe what you would actually use in practice, because you are interested in amplitude, but you also are interested in not complicating the simulation. So one thing I like to steer people away from, including myself, is introducing unnecessary complexity. The point of experiments is to get to a simulation, and also the point of simulations are just to understand an aspect of the experiment, not encompass all the potential types of behavior and that may occur. Just the simulation to describe enough that you have a decent idea about what the performance is going to be like. I also discuss application of a dissipation boundary. This is not particularly necessary. You can, usually your transducer is always interfacing with something else, and that something else is always going to be, taking part of the energy away from the transducer, which is what we want, because we want the transducer to be doing work or giving ultrasonic energy to an external environment, which can be many different types. It could either be like a water domain, or it could be like you're doing surgery on tissue, so you're ablating tissue, or you're doing ultrasonic welding. A lot of those are different in what you're intending for the ultrasound to do, but nonetheless, it has to leave the transducer and enter your new domain. And yeah, if there's time, we'll talk about damping theory a little bit, because elastic damping is not really taught in school, because you can't easily model elastic damping with a dashpot. Does not model elastic damping. You actually have to use an imaginary spring constant, which we all love math, right? Engineers, we all love imaginary math too. And that's how you actually have to handle elastic damping. Basically, as something stretches, it then the work that you put into to compress a material is not the same that you actually are allowed to extract back out when you pull back, let's see, on that spring, and the spring is now doing work on your hand. So that's basically what we're after. So all the damping of materials that we're going to be using here are basically elastic damping based. So they are when the spring or material compresses and expands, that there is energy that's lost in that process when it's converted to kinetic energy, or it's doing work on the other components or the other surrounding elements, you could say, for finite element analysis. So all right, this is obviously not true, I don't have a dog, but what's the importance for damping for simulations? So just make sure I have some notes here. So basically, piezo materials, piezo ceramics especially, can respond at up to gigahertz frequencies. Right? They can produce ultrasound or megahertz and gigahertz frequencies. However, the displacement is small, up to all the way kilohertz too, because that's what we usually use, many of us. But there's they have very low displacement. So in order to increase displacement, we use resonance. Basically, this is a very simple kind of concept. And resonance is a frequency at which energy stored, base energy is stored efficiently, you could say, is stored. There's many ways to define it. I think using all the different terms helps us to really kind of get a good understanding. So resonance is a frequency at which energy is stored efficiently in a system. Or I guess you could say transferred, but basically transferred, I guess maybe I'll say and stored efficiently in a system. Basically the amplitude, so as you increase energy, displacement, or amplitude increases. All right. And that's what we want. We want that displacement. We had this problem here, and now we have the solution here. Okay, that's great. We have this energy increasing. So basically the steady state response is going to depend on, one, how much energy you can put in per cycle. And this is actually constant, like pretty much constant. Like it depends on your voltage and your piezoelectric charge coefficient, and basically what kind of mode you're exciting. That's what the how much energy you put in. But how much, and then it also depends on, damping, which increases with amplitude. So, you have two opposing things, your energy you're putting in, and eventually at some point, the damping kind of meets your energy. And that's what the steady state response actually is. And that's what we end up getting. So this is a huge aspect. And damping also varies, basically. Damping also varies orders of magnitude. So if you put the wrong damping in, you can easily get like twice the amplitude or half the amplitude or 10 times the amplitude that you actually expect. Now there are also ways to analyze transducers without damping. We have eigen, frequencies and basically modal, just pure modal analysis. But we do like to look at, exciting the piezo crystals, getting oscillation levels, and we want it to be relatively relatively accurate for the most part. So this is why we must model damping correctly, because it can vary orders of magnitude, and it's linear with that. Like if your piezo charge constant changed by a factor of 2, which you would kind of, in rare cases would you ever kind of mess with the charge constant a factor of 2, but damping can change, as you'll see in the presentation, by a factor of like 4 or 5 easily within kind of a similar example with just by changing loading conditions. So it's really important to get right or understand what is affected when you get damping wrong, because you can also get damping completely wrong or not even use a damping coefficient, but then you're interested in something like, microns per milliamp, for example, for a resonant transducer, or for anti-resonant transducer, you maybe interested in, volts for, microns per volt, getting analysis like that. But in general, you do want to look at damping, and that gives you the right amplitude. And especially for some devices which are intentionally damped, like acoustic transducers specifically, those are specifically, intentionally damped in order to very improve bandwidth and other response characteristics. So in those cases, I won't be necessarily specifically speaking to that. There's not going to be a whole lot of stuff on polymers and backing materials here today, or specific damping materials. We're going to be working with a cleaning transducer. But some of these concepts can apply, and I can also describe where they don't apply. So I'll mention that metal and ceramic, basically hard components, are mostly elastically damped. But like things like, polymers and other such materials, softer materials, they also have damping according to, for example, strain rate, how fast things are deforming. So it's a little bit more complex, you could say, or just additional components to be added there. But many of us do work on just, metal components. So I'm analyzing this specific transducer in 2 cases, one where it's just sitting on top of a piece of foam, and one where the transducer is loaded with a 6-pound weight, just to kind of balance on top of it. This is not a fancy experiment, and it's not a completely accurate one, but it's also just something to help us get through this analysis. I don't always have things laying around that like this is a perfect thing or something that the clients use. So I can't really kind of show that. So this is something simple I could show, and you can extrapolate this type of analysis to any operation of a transducer that you characterize in low power and high power, and you also characterize loaded and unloaded, and their specific important ideas. What I really want you all to capture here today is the kind of the thought process. There's no right or wrong way exactly. There's just a way that's useful and the way that's not useful, and ends up, so that's the kind of thing, that's the kind of way I go about things. So hopefully you'll get the idea about how this is to be done. They're not specific rules per se about how you apply damping, but there is a theoretical kind of understanding, and also how useful and error prone the approaches you take might be. So kind of proceed at your own caution. Sometimes this is useful just to avoid this whole damping thing altogether, and just say, damn with the damping, like let's just analyze eigenfrequencies. That is actually a really great way to work. But it is useful. to show, you know, colleagues, you got your impedance analysis going like this, and then you got your transducer analysis. Oh, look how they match. Everything lines up, and it's a good feeling to be able to model amplitude as well, because that is important. So we have the experimental methods. We have the function generator for the high power, which is not really high power. See, again, this is one of my kind of, I'm using amplifier. I'm not putting, I don't want to say too much effort, but I'm not making it too real, but I just want to get you a flavor about, hey, you could, instead of providing, I think I end up providing like 7 volts or something, you could do like 70 or 700, depending on what your device is. Use the same type of analysis and it works. So in this kind of video here, I did the impedance analysis to get the quality factor, and I made it into a video format, so we could kind of just go through it, and it's about 2 minutes long, so I think we'll be okay. So you know, first we take the sweep of the transducer sitting on foam. This is the transducer in air. What's actually true here is I don't use perhaps enough points. So I did that. Kind of showing you the quality factor is 400. If you can read that down there in the corner, it's kind of small. I'm changing the axes to real admittance, conductance basically, and real impedance, resistance. But I don't think I really need to do real impedance, because, well, let me just stop this here, because I'm just interested in the resonance frequency. There's a lot of talk about losses between resonance and anti-resonance. I'm not getting into that. I don't think that that's necessary for most practical situations. What you'll see here is me trying to, you know, I'm just showing you the quality factor calculation again, is when you take the conductance or the real admittance, you take the maximum value, which is going to be the resonance, and you do the half power bandwidth. So you find the half the value of the maximum, and then you divide the resonance frequency with the bandwidth between the half power, basically half the maximum admittance. And this is just a process of me showing that for you, and I'm kind of locating it a little bit more closely. And I think I realize I have to take more points because it seems very sparse. So what looks nice in a wideband range, you may be actually skipping a lot of points. I recommend interpolating. That works very well. But also, you might as well not interpolate if you can just take the data a little bit more finely. I think I use 2 Hertz and I go to a smaller range. So this is an important consideration for us who are measuring properties, who may be looking for small changes. And if you are looking for small changes, then you need to be measuring it with a bit more precision. So let me just go ahead, and here I have that peak, and I measure the quality factor by finding the half power bandwidth. I think I've shown it before. Now it increases to 463. So yeah, it started at 400 and it became 463 at the end. Now in practical situations, that is actually not a significant difference. If you built 2 transducers, one had a quality factor of 400, one had 450, those are practically the same, because damping varies so much, and to even have that similarities is pretty good actually. So yeah, so here was that video. It was actually here. The unloaded Q was actually about, what did we say it was, about 450. I think when I was taking data after I made the video, I chose the first one. It's 463. And it's about 450. So now I loaded it, and then I found the quality factor of the loaded condition to be 165. And I did that same thing with the real, admittance, which is the blue, impedance, which is the red. And I got the quality factors, basically. All right. So then I use the high power function generator, not really high power. So I did first the unloaded case, where I'm using a larger voltage than the impedance analysis section in order to simulate or demonstrate, like, hey, we use a larger voltage, we get more losses, but we don't have access to like an impedance analyzer that does high voltage sweeps, or because even high voltage sweeps are going to be nonlinear. I haven't talked about that yet, but if you do a high voltage constant voltage sweep over the resonance frequency, you're going to get a nonlinear impedance response, because impedance actually most closely is linear most closely to either power input, or it's most closely linear with velocity output or displacement output, if you can control that across the sweep. Because you can't, in most cases that, you can control feedback loop, and the program that I had does that. It can linearize your response basically by controlling the output to which it's linear to, which is either power or displacement or velocity. But in this case, I'm not doing that. I'm doing like you might in the laboratory, where you just have your impedance analyzer, and then you go to your like application circuit, and it drives it. It gets to that zero phase. It drives that at resonance. So how do you deal with that? Right now, I'm actually manually changing frequency by hand. You can see the frequency down here is 39.9 kilohertz or so. And then I kind of get things in phase. See, that's about in phase, right there. So then I record the RMS voltage, which is 221 millivolts here, and I can record the RMS current, which is taken over a resistor. So you have to divide that, or you multiply, actually divide it by 10. Sorry, I think you divide it by 10 to get the current. Oh yeah, actually no, it's multiplied by 10. So because it has a resistor, the current is multiplied by 10, the voltage. So you have to divide by 10 in order to get back to the current. And then here, then I just calculate, hey, here's the voltage, here's the current, and then that's the impedance. And actually it wasn't 544. Actually, no, it was 541. All right, so then I put the loading condition. Now with the load, I put the load on, I think here. There, I put the load on, and then I have to increase the voltage in order to get right to the same current. So here's an important part here. This is really important to understand. When you're comparing a loaded and unloaded transducer, you have to compare it for the same output, mechanical output of the crystals. So the crystals have to be operating the same way. There has to be the same kind of displacement throughout in order to make these two comparable conditions. So because the comparable condition is going to be velocity dependent, or not power dependent, because power now is going to depend on load. Basically, most of us know that if you keep the current constant at resonance, or the voltage constant at anti-resonance, despite the load, you'll get the same level of oscillation at the end of the transducer. That's the constant that we're going to map here. So what I actually did, after putting the load, I varied the voltage until I got to the same current. So now I can compare the two cases. So this is the case under the same transducer excitation, not voltage excitation, but actually displacement excitation. I can calculate the impedance in both cases. So right, I've varied the voltage in order to get the same current, so I can compare impedance values. And there's a reason I'm doing this, is because you can actually use ratios very effectively to compare low power quality factors and high power quality factors. That's why I'm doing this all, because why I'm calculating voltage and I'm trying to keep the constant condition, because the difference between these two is only the load. It's not the displacement of the transducer itself. Now, there are kind of a lot of other nuances, but we do the best we can, basically. And this is the best we can do. So here are the kind of the summary parameters for low power and high power, loaded and unloaded. Sorry, loaded and unloaded. So the quality factor is actually 450. I'll put star 450. I think I recorded it first as 400. That would make a difference in the analysis, but it's not going to make a difference in our discussion about how we do it. And I'm using the real admittance here, which if you actually manually set the phase to 0. Now, it's not always going to be 0 for some transducers, and that gets a little more tricky. Not too tricky. I think you just have to continue to find that same real admittance in driving conditions. I believe that's probably the right way to do it. Just find the same admittance with the same phase or something like that. But for now, we're just talking about 0 degrees phase. Maybe I'll have another blurb about what to do when you don't have when you can't easily find you vary the transducer until you get to the right power. It's something like that. I'm not gonna kind of consider it on the fly today. So yes, for these transducers that easily do get to 0 degrees phase, where it's really obvious where the maximum power is going to be drawn, you can find the real admittance, basically the inverse of the impedance at that point. If there's an insignificant kind of capacitive part to the resonance, which there is for this transducer because it's a high Q transducer, relatively high Q. Let's go back here. These are just pure measurements, low power Q. If you look at the ratios here between Q and the real admittance in these two cases, they are very similar. Now they'd actually be they're very similar. It actually would be about 2.6 with this new quality factor I have here. But they're very similar, meaning that basically we can track the real admittance or perhaps the impedance if you want to go that route with the quality factor. So that's all that's changed. We do see the frequencies are the same, but just the loading has changed. Now, when the frequency shifts, that's another kind of like, not problem, it's another kind of challenge because you have to add stiffness and damping. In this case, there's practically only damping added when you add that load. You know, some of the ultrasound goes through into the kind of weight, and some of it bounces back, but there's not it's not adding dynamic stiffness or dynamic mass, oddly enough, right? You put a 6-pound weight on top of the transducer, it adds no dynamic mass. How can that be? Well, it's not, the interface stiffness is very low. So therefore it's a pathway to lose energy, but it's not a pathway to kind of bounce back. Nothing from that weight is probably bouncing back and coming to the transducer and kind of continuing to resonate. Hope that's clear. So this high power case where I used, what was it, higher voltage, 1.2 volts, I think I said at the end. Where is it? Yeah, I use 1.2 volts, and this is kind of I guess a pretty lame high power measurement. These are sort of doctored. I'm not going to say how, but they're sort of doctored by accident. But I'm just giving you something that you can use for food for thought for analysis later. So the high power Q, we don't know because we just got admittance, right? We don't have this value. So what I did was that we do have we just have real admittance, and we have the frequency. We can also see that the frequency is relatively the same. Now, higher voltages and higher power are naturally going to shift lower. It doesn't necessarily mean it's damped. It just means there's a little bit more. There's more. The elastic components are slightly softer at higher voltages. Ceramics are also known to reduce the resonance frequency as well when you increase amplitude. And same thing with I think metallic components. They also do reduce in stiffness when you increase amplitude of displacement and stress and strain. So what we have here, there's a comment, and I'll get to those comments as soon as I finish this slide here. So I can calculate the Q based on the admittance ratio, and I'm calculating the ratio from this from the initial one, you know, from the low power unloaded. So from that ratio, then I calculate the quality factor. That's pretty nice, right? You usually don't get a quality factor when you're doing application experiments, but you can if you make relative assumptions about how they track. And I did the same thing here. And I calculated the Q from the other loaded case. I calculated the ratio, then I just divided that ratio by the quality factor here, and I was able to get a quality factor of 147, which isn't too different, but it is lower, and it has a slightly lower frequency. We don't need to, and basically if the frequency changes a lot, you have to add stiffness and mass somehow. Basically, if the quality factor decreases, if the frequency decreases a lot, then you're going to have to add some mass. If it increases for a particular reason, then you're going to have to add stiffness. That's usually not the case, though. Usually when you do load in loading situations, you do increase, unless you are like maybe ultrasonic welding, where you're very firmly against a very hard surface, and you do have some increase in your frequency. You're gonna have to add stiffness. Probably not mass. It depends on what your anti-resonance frequency looks like. But this is a good start at least. So there's some comments. Yeah, somebody asked, hey, it'd be nice to see the setup of the model. Yeah, if we have time, may not seem like it though. And can you explain a little bit under what circumstances the transducer is considered to be loaded or unloaded? Unloaded just means sitting on foam, basically. Or you could say it's like sitting in the clamp, however you'd like to kind of consider the base condition. That's where you're going to start measuring loss factors. Then when you add the mass or you add the load, you put it under, put the transducer under, surgical transducer, you put it underwater to simulate some type of, response or damping in realistic scenarios. In that case, that would be loaded. It's kind of up to you, the engineer or the scientist. So if you had glued a mass, then you expect a change in frequency? Definitely, yes. Because it's also, the interface is rubber, like that mass had rubber on it too, and there's interface stiffnesses. So yeah, if you glued it, that's a perfect, and it was a perfect joint, then you wouldn't have to really do that. You wouldn't, you would have definitely frequency shifts. Yeah, the way I connected the mass, which is I just put it on top and I balanced it. It was it was kind of easy. So somebody asked, can you explain what's the quality factor? So yeah, I can explain that real quick. So if you look at this impedance resonance, this is an LCR resonance. So a resonance has an amplitude at the maximum, right? So there is like a non-dimensional loss factor associated with all resonant systems that indicate that the maximum response, and and if we're looking only at the real part, so let's do just impedance. So the maximum, or in this case, if it's impedance, it's a minimum. If you go, if you increase, if you get away from the resonance point, if you either are using non-real values, or it's kind of confusing, but basically the spread dictated in this way is representative of how much damping there is. If there's more damping, this peak would be more spread out. If there's less, it'll be more sharp. And there is a specific bandwidth related between the half of the maximum, related to how those relate to damping. So in this case, you would take 39.7 kilohertz and divided by, let's say, like 200 hertz, like this bandwidth over here, and then you would get a number. In this case, that number is 165. So that's the quality factor. I'd recommend you search that up. You may also kind of search other videos or previous recordings on that. But it's important. Quality factor and understanding what damping is very important. The quality factor is specifically a non-dimensional value about how a system is damped according to elastic factors. You can also calculate it for viscous damping cases, but it's not uniformly true over all frequencies. There's specific, I guess, beauties about elastic damping, which makes us free to use it in real life. Although it's not the first type of damping we're introduced to in kind of college or graduate school exactly, and with viscous. So all right, so I will probably jump through the model pretty quickly, but I do want to show that for sure. So here's a transducer. It's not this actual one. I just try to measure it and draw it out. And here it is in COMSOL. Here it is meshed. I'll be sending these notes out later, but here's the model tree. Basically in COMSOL, it's a 2D axisymmetric model. Okay, oops, here we go. It's a 2D axisymmetric model. And I have inserted damping for the materials, and I'll explain that, but that's kind of how I set it up. It is a, I did eigenvalues and also the frequency response. But let me just go ahead here and show you how loss factors are implemented in COMSOL in the best way for piezoelectric devices, especially those with mostly considering hard materials as the majority of the loss area. So I think I derived this a while ago, or I found this somewhere. I think I may have derived it, but basically the loss factor that's implemented in COMSOL, you right-click the linear elastic material or piezoelectric material, then you select isotropic loss factor. The loss factor not depending on any specific direction. We know piezoelectric materials are highly anisotropic. However, it is not useful to think about them to implement those values and having, losing hair. As you can see, I haven't lost my hair. I have not lost hair over implementing anisotropic losses. Use isotropic losses, and that's going to be the most similar. I can, and there's a comment about the quality factor. I'll do a quality factor calculation after in the Q&A, just so you're clear, because it's important. But basically, just know that something about the sharpness of the peak, and it's just, it's a simple thing, and I'll just explain to that afterwards. So you can get the loss factor for the material, and if you put the loss factor for the material, you get, and you assign every material the loss factor according to 500Q. Guess what's going to happen when you do your impedance analysis, or you make impedance on COMSOL? You're going to get a Q factor of 500. Like, that's just in it. What goes in must come out. That's the easy part, and that's a lovely part about isotropic loss factors. They just always work. For assuming you're only considering your specific scenario. See fine print for details. ANSYS also has something similar. Now, it requires you to make this like ADPL code. And this is a link from one of the forums. But basically, you have to do something where you define. This is, I think, the name of the component, and this is how the loss factor is implemented. I think it's directly 1 over the quality factor. So I had a lot of stuff to talk about losses. I'm glad I didn't get into that, because this is also taking a long time. So let me get into the model and how I approach the model first. And that it's like this. Part 1, low power and high power unloaded. I look at it like that. And then I go to this part 2, determine the dissipation boundary loading. That's the boundary where I put the weight, which didn't add any mass, but it added damping actually. So here's how it worked. First step I did, I assigned Q for all the materials, the piezo and elastic, for low power unloaded Q. So that same Q, which is like about 400, I assigned that for all the materials. Now you may be saying that, well, steel and aluminum have much higher quality factors than crystals usually. And in this case, it was obvious from the quality factor of the device that it was PZT4, because the quality factor ended up being like 400-ish. For PZT8, it'd be like usually 800 or higher, typically, for metal, ceramic, Langevin transducer. But I assigned it all because it doesn't exactly matter how you apply it, as long as they're still on the same order of magnitude, because the wave is going to go like 400 quality factor. Let's say the wave goes 400 times back and forth, and it bounces around 400 times before it like gets, reduces in amplitude significantly. So it's going through all the components, so it's getting damped by everything. It's not really, at this point, it can be in some cases, because you can have a horn sometimes, which has inordinate amount of stress in it. But for simplification and for usefulness of analysis, I start off with all the materials at the same quality factor. And I just use, again, this equation, 1 over 2 times 450. And in the COMSOL, I have that monitored right here, 1 over 400 times 2. And there's a value that comes out. This is the one that I use for the first case. Then I adjust the quality factor to match the high power unloaded quality factor. So then I add extra damping to, I assume all the crystal, all the damping that comes from driving at higher power, it comes from the crystals, the extra damping. And is that a good assumption or not? That's up to you to decide, honestly, because there is a little bit more damping that happens in metals as you drive them harder, but they're usually much higher in quality factor, and like even tens of thousands in the terms of quality factor, where crystals are usually at the maximum 2,000, and for any practical purpose they start to be 1,000 and less when you actually drive them with any amount of voltage or power. So really, a lot of the losses are probably going to be best represented by the crystals and the interfaces. Basically, the crystal, the electrode, the crystal, the electrode. Those interfaces actually have a lot of damping. You could put damping everywhere you look. Add a little damping, sprinkle a little bit there, sprinkle a little bit, like, let's put a little damping on this interface, a little bit of that, a little bit on the screw threads. You could do all that, but what's in the end, the wave is going to go back and forth, back and forth, back and forth, and it's not going to matter. It's not going to give you a big difference unless you're trying to create like a universal analysis, and that's a little bit more science than it is engineering analysis for specific cases, because engineering analysis really, we want to be practical, and we want to describe the situation that we have in front of us in the best way. And that's done by some amount of intelligent calibration. So what does that look like basically? Unfortunately, this can't get larger on the screen, but I started off with, this is the piezoelectric loss factor that I started off with, 1/400 times 2. And here's elastic losses, and I put the elastic ones here. So these are all defined with the same loss values. This is pretty much the same. You could, the piezoelectric, I had put in that parameter. Then what I did is I created like a parametric study where I varied. In this case, this was a little bit different, but I varied the piezo loss, and I kept increasing it until it met the quality factor. Now, quality factor is kind of annoying would be annoying to calculate from such simulations. I think people can agree, like, nobody wants to go in your simulation and like pick out 3 points and calculate the quality factor. Maybe you could automate it, but an easier way to get the quality factor is just make sure that your impedance is your real admittance or impedance is the same at resonance as it is in the model. So you should, an easy way to do this, if you're like forcing it to happen, you can just go to your basically your coupling, your what do you get here, your charge coefficients. You just so basically what I do is to you can match impedance ratios instead of quality factor ratios. Kind of the same thing I did here. Let's say your impedance in your simulation was different than the one you had in your experiment. And you could change your charge coefficient to match the impedances, and that would be a good way of doing it. Or you could just find a ratio, like in my experiment, a reduction in admittance by a factor of 2 is a reduction in quality factor by a factor of 2. Yeah, so I just did that. I just did the relative ratios. I didn't exactly calculate the quality factor at every step. That would be kind of annoying to do. But in very low losses, very high losses, quality factors, let's say less than 5, you'd need to do that, something like that. But in this case, high quality factors, I'm just using scaling. So I basically varied the piezoelectric material damping, and I got a new factor for the high power case. And the new factor was 0.0024. So it was about twice. I had to double the losses for the crystals in order to get from this value, 398, to 288 for the whole system. So I doubled the losses in the crystals. And it happens like this. This is a different scenario, but basically you're adding losses and you're dropping your admittance. And I basically found those admittance ratios. That's how I did things. All right, we're going close to the end. The next part is, so then therefore I got my high power piezo loss factor, and I also have loss factors for the metal components. But I just sprinkle a little bit more in the crystals because they do tend to have much more losses than metal components do. Next, in order to do the boundary dissipation, I added a boundary dissipation kind of interface. And what I did in COMSOL specifically, and there's probably a similar example, and this is not a trial. I have a trial version of COMSOL, but I have actual like a real version, but I'm just testing out some extra features, extra modules. So I needed the trial for now. Oh well. So I'm legal to work at COMSOL, by the way. So that's what I'm saying. Yeah, so what I did here, I added a low reflecting boundary here because we added that load, and we know that load didn't change the frequency at all. So it's just losses. It's not any mass or stiffness. Or you could have added some mass and stiffness, like you could if you could add a fixed mass, or you could add another material on the end, whatever you think is the best part, the best way to do it, and you test it using a few conditions and experiments, you implement it that way. If you want like a line mass, or if you want a distributed weight on top, it's up to you. I could have just easily put a 6-pound weight and have an interface which depends on the weight and the rubber, and the rubber of the weight, and the transducer interface, but no thanks right now. I'm doing something a little more simple. So I defined a low reflecting boundary here that's typically used for like water, but usually it comes off, I think if you make a new low reflecting boundary, and we're about done right now. It just comes out like this is the normal setting. You do user defined, and again, I did isotropic, and I put a varying. So this is like perfect transmission. But you don't have perfect transmission. We don't have everything that hits this doesn't just leave. You would have an extremely low quality factor if all the energy that went to the front just leaves. So I put a calibration factor, B loss. So I varied B loss. So this is, I think, the mechanical impedance. So I varied the B loss basically. So changing the mechanical impedance of this interface or this low reflecting boundary, then to actually reflect some things back. So I decreased it. And this is what this is actually right here. 1, 2, 3, 4, 5. Oh, I have that 1, 2. There it is. So this is what actually I'm doing. I actually increased this B loss to hit the admittance, which I expected the quality factor that I wanted to be at. So I end up changing this value from 0.001 all the way down to 0.003. And I think the admittance that correlated with the best value, I have it was 0.0045. So that's how I actually added losses. And I think that stuff is still here, so I can just pull it out. Not a neat file, I would have to say. That's let me just make it all impedance like for you guys. Despite all the talk I do about the real components, I still like the other values. I still like to use absolute impedance. So yeah, this is what happens to the quality factor at resonance as or the impedance at resonance. And as you see here, the minimum according to like the bandwidth, let's say, is going to be less and less as the impedance decreases. The bandwidth is also going to widen too. So that's what losses are. That's what those losses are doing for me. There may be other ways of doing it. And there's other ways of adding interface losses and other types of viscous losses. I think there's not enough time nearly to discuss all of that. But I think I'm going to start going through and kind of come to the end for questions. And I'm going to kind of stop this recording. All right. Thanks for joining in. And I'm going to stop the recording.